Welcome. Today we're diving into the FP growth algorithm, a powerful tool in data mining for discovering frequent patterns. Unlike older methods, FP growth is known for its efficiency and speed, especially when dealing with large datasets. In this video, we'll break down how FP growth works, why it's important, and where it's used. Whether you're a data enthusiast or just curious about how machines find patterns in data, this journey will give you a clear understanding of FP growth and its real-world applications. Let's get started by understanding the basics of frequent pattern mining. Frequent pattern mining is a foundational concept in data mining. It involves searching for recurring relationships or patterns within large datasets. For example, in a supermarket, frequent pattern mining can reveal which products are often bought together. This information is valuable for making business decisions, such as product placement or targeted promotions. The challenge lies in efficiently finding these patterns without scanning the data repeatedly. That's where algorithms like FP growth come into play, offering a faster and more scalable solution compared to traditional approaches. As datasets grow larger, traditional pattern mining algorithms like apriori become less practical due to their high computational cost. These methods often require multiple scans of the database, which can be time-consuming and resource-intensive. The need for a more efficient approach led to the development of the FP growth algorithm. FP growth addresses these challenges by using a compact data structure and minimizing database scans, making it ideal for handling big data scenarios. Next, let's see how FP growth achieves this efficiency. FP growth and apriori are both popular algorithms for frequent pattern mining, but they differ significantly in their approach. Apriori generates candidate item sets and repeatedly scans the database, which can be slow. In contrast, FP growth compresses the database into a tree structure and avoids generating unnecessary candidates. This results in faster processing and less memory usage. Understanding these differences helps highlight why FP growth is often preferred for large-scale data mining tasks. The heart of FP growth is the concept of compressing the dataset into a specialized structure called the FP tree. This tree captures the frequency of item sets in a compact form, allowing the algorithm to mine frequent patterns without generating all possible combinations. By focusing only on relevant data, FP growth significantly reduces the computational burden. This core idea is what makes FP growth stand out in the world of data mining. FP tree, or frequent pattern tree, is a compact data structure used by the FP growth algorithm. It organizes transactions in a way that common prefixes are shared, reducing redundancy. Each node in the tree represents an item and its frequency. By traversing the FP tree, the algorithm can efficiently identify frequent item sets. This structure is key to FP growth's speed and scalability, especially when working with massive datasets. Constructing the FP tree involves two main steps. First, the algorithm scans the dataset to determine the frequency of each item. Items that do not meet the minimum support threshold are discarded. Next, the dataset is scanned again, and transactions are mapped onto the FP tree in order of item frequency. This process ensures that common patterns are grouped together, making it easier to mine frequent item sets later on. Initial scan of the database is all about counting how often each item appears. This step is crucial because it helps the algorithm decide which items are frequent enough to be included in the FP tree. Items that don't meet the minimum support threshold are ignored, which streamlines the tree and focuses only on the most relevant data. This filtering process is the foundation for building an efficient FP tree. After filtering out infrequent items, the algorithm performs a second scan of the database. This time, each transaction is mapped onto the FP tree with items arranged in descending order of frequency. This ordering ensures that common prefixes are shared, which compresses the data and makes the tree more efficient. The result is a compact FP tree that's ready for mining frequent patterns. Key component of the FP growth algorithm is the header table. This table keeps track of each frequent item and points to its occurrences in the FP tree. By following these pointers, the algorithm can quickly locate all transactions containing a specific item. The header table streamlines the mining process and is essential for efficiently finding frequent patterns. Once the FP tree and header table are built, the algorithm begins mining for frequent patterns. It starts from the least frequent items and works its way up, constructing conditional pattern bases for each item. These bases are then used to build conditional FP trees, which reveal deeper patterns within the data. This recursive approach allows FP growth to efficiently uncover all frequent item sets. Conditional pattern base is a collection of paths in the FP tree that end with a particular item. By extracting these paths, the algorithm can focus on the context in which an item appears. This targeted approach helps uncover patterns that might be missed by broader searches. Conditional pattern bases are a key innovation in the FP growth algorithm, enabling it to mine patterns efficiently. After identifying a conditional pattern base, the algorithm constructs a new, smaller FP tree called a conditional FP tree. This tree represents the subset of transactions relevant to a specific item. By recursively building and mining these conditional trees, FP growth can efficiently discover all frequent item sets without redundant computation. This process is repeated for each item in the header table. FP growth algorithm uses recursion to mine frequent patterns. For each item in the header table, it builds a conditional pattern base and a conditional FP tree, then mines that tree for patterns. This process continues until no more frequent patterns can be found. The recursive nature of FP growth allows it to efficiently explore all possible item sets without unnecessary repetition. FP growth offers several advantages over traditional pattern mining algorithms. It requires fewer database scans, uses less memory, and is much faster, especially with large datasets. Its tree-based structure compresses data efficiently, making it ideal for big data applications. These benefits have made FP growth a popular choice in both academic research and industry. While FP growth is powerful, it's not without limitations. The algorithm can struggle with datasets that have a very large number of unique items, as the FP tree may become too complex. Additionally, constructing and managing multiple conditional FP trees can be resource-intensive. Understanding these limitations helps in choosing the right algorithm for a given problem. One of the most common applications of FP growth is market basket analysis. Retailers use this technique to discover which products are frequently purchased together. By analyzing transaction data with FP growth, businesses can optimize product placement, design targeted promotions, and improve inventory management. This real-world use case demonstrates the practical value of frequent pattern mining. FP growth is also used in web usage mining to analyze user behavior on websites. By identifying frequent navigation patterns, website owners can improve site structure, personalize content, and enhance user experience. This application highlights the versatility of FP growth beyond traditional retail scenarios. In bioinformatics, FP growth helps researchers find frequent patterns in genetic data. These patterns can reveal important biological relationships and aid in disease research. The algorithm's ability to handle large, complex datasets makes it a valuable tool in scientific discovery and medical research. Recommendation systems use FP growth to suggest products or content based on user preferences. By mining frequent item sets from user data, these systems can make personalized recommendations that enhance user satisfaction and engagement. This approach is widely used in e-commerce, streaming platforms, and social media. Financial institutions use FP growth to detect fraudulent patterns in transaction data. By identifying unusual combinations of activities, the algorithm helps flag potentially suspicious behavior. This proactive approach enhances security and protects both businesses and customers from financial fraud. In healthcare, FP growth is used to analyze patient records and discover patterns in symptoms, treatments, and outcomes. This information can guide clinical decision-making, improve patient care, and support medical research. The algorithm's efficiency makes it suitable for processing large volumes of healthcare data. Text mining applications use FP growth to find frequent word or phrase patterns in large document collections. This helps in tasks like topic modeling, sentiment analysis, and information retrieval. By uncovering hidden structures in text data, FP growth supports a wide range of natural language processing applications. Network security professionals use FP growth to analyze logs and detect frequent patterns of suspicious activity. By identifying common attack vectors, organizations can strengthen their defenses and respond more effectively to threats. FP growth's speed and scalability make it a valuable tool in cybersecurity. Manufacturers apply FP growth to analyze production data and identify frequent patterns in equipment usage, maintenance, and defects. This insight helps optimize operations, reduce downtime, and improve product quality. The algorithm's ability to handle complex, high-volume data makes it ideal for industrial applications. Telecommunications companies use FP growth to analyze call records and network usage patterns. This helps in detecting fraud, optimizing network resources, and enhancing customer service. The algorithm's efficiency enables real-time analysis of massive datasets, supporting better business decisions. Social network analysis leverages FP growth to find frequent patterns in user interactions, such as likes, shares, and comments. These insights help platforms understand user behavior, improve engagement, and design better features. FP growth's scalability is crucial for analyzing the vast data generated by social networks. Supply chain managers use FP growth to analyze transaction and logistics data, identifying frequent patterns in orders, shipments, and inventory. This helps streamline operations, reduce costs, and improve delivery performance. The algorithm's ability to process large, complex datasets makes it a valuable asset in supply chain optimization. Energy companies apply FP growth to analyze consumption patterns and optimize resource allocation. By identifying frequent usage trends, they can forecast demand, reduce waste, and improve sustainability. FP growth's efficiency supports real-time analysis and decision-making in the energy sector. Educational institutions use FP growth to analyze student performance data and identify frequent patterns in learning behaviors. This helps educators tailor instruction, improve outcomes, and support at-risk students. The algorithm's scalability makes it suitable for analyzing data from large student populations. Sports teams and analysts use FP growth to find frequent patterns in player performance, game strategies, and outcomes. These insights inform coaching decisions, player development, and game planning. The algorithm's ability to process large volumes of data quickly is a major advantage in the fast-paced world of sports. Transportation companies use FP growth to analyze travel patterns, optimize routes, and improve service efficiency. By mining frequent patterns in trip data, they can reduce costs, enhance scheduling, and provide better experiences for passengers. The algorithm's efficiency is key for handling the vast data generated by modern transportation systems. Retailers use FP growth to design effective promotions by analyzing which products are frequently bought together. This helps create bundled offers, cross-selling strategies, and targeted discounts. The insights gained from FP Growth drive higher sales and customer satisfaction. Businesses use FP Growth to segment customers based on purchasing patterns. By identifying groups with similar buying habits, companies can tailor marketing strategies and improve customer retention. This targeted approach leads to more effective campaigns and stronger customer relationships. Insurance companies apply FP Growth to analyze claims data and detect frequent patterns in policyholder behavior. This helps identify risk factors, prevent fraud, and design better insurance products. The algorithm's speed and accuracy are valuable for managing large volumes of claims data. Inventory managers use FP Growth to analyze stock movement and identify frequent patterns in product sales. This helps optimize inventory levels, reduce stockouts, and minimize excess inventory. The algorithm's efficiency supports real-time inventory tracking and decision-making. Financial analysts use FP Growth to uncover patterns in transaction data, market trends, and investment behaviors. These insights support better decision-making, risk management, and portfolio optimization. The algorithm's ability to process large financial datasets quickly is a major advantage in the fast-moving world of finance. E-commerce platforms use FP Growth to analyze customer purchase data and recommend products. By identifying frequent item sets, they can personalize shopping experiences, increase sales, and improve customer loyalty. The algorithm's scalability makes it ideal for the high-volume data generated by online shopping. Cloud service providers use FP Growth to analyze usage patterns and optimize resource allocation. By mining frequent patterns in service requests, they can improve performance, reduce costs, and enhance customer satisfaction. The algorithm's efficiency supports the dynamic demands of cloud environments. FP Growth is increasingly used in real-time analytics to process streaming data and identify patterns on the fly. This enables businesses to respond quickly to emerging trends, detect anomalies, and make data-driven decisions in real time. The algorithm's speed and scalability are essential for modern analytics applications. Mobile app developers use FP Growth to analyze user behavior and personalize app experiences. By mining frequent patterns in app usage, developers can design features that better meet user needs and increase engagement. The algorithm's efficiency makes it suitable for processing large volumes of mobile data. Environmental scientists use FP Growth to analyze sensor data and identify frequent patterns in environmental changes. This helps monitor pollution, track climate trends, and support conservation efforts. The algorithm's scalability is crucial for handling the vast data generated by environmental monitoring systems. Smart city initiatives use FP Growth to analyze data from sensors, transportation, and public services. By identifying frequent patterns, city planners can optimize traffic flow, improve public safety, and enhance urban living. The algorithm's efficiency supports the complex data needs of modern cities. The Internet of Things, IoT, generates massive amounts of data from connected devices. FP Growth is used to analyze this data and find frequent patterns in device interactions, usage, and performance. These insights help optimize IoT systems, improve reliability, and support predictive maintenance. Wrap up: the FP Growth algorithm is a fast, efficient, and versatile tool for frequent pattern mining. Its tree-based approach and minimal database scans make it ideal for big data applications across many industries. As data continues to grow, FP Growth will remain a valuable asset for uncovering hidden patterns and driving data-driven decisions. Thank you for joining this exploration of FP Growth. Stay curious and keep exploring the world of data mining.